here. A year and a half ago, we were thinking about this project, actually we're thinking of it literally in a vacuum. We didn't have any experience with the situation in South Africa or other countries. And so a lot of the ideas were actually homegrown, if you will. And about a month ago, we found out that a lot of these ideas were already being tested and being done here, particularly with the steel screw. So it's a little bit of rediscovering or reinventing the wheel, but hopefully with some modifications. So this is the question that has been asked: what happens when pits fill up? And obviously, you have a nice vacuum tanker, nice vacuum truck, then you can access the sites. Then it's maybe an easy solution for those pit toilets or little bit wet sludge. But we have problems with affordability, and we've seen talks about that, about business models, and problems with accessibility. How do you get into these crowded, narrow walkways? And obviously, if you have these problems, the most common way, as we've seen today, is manual waste extraction. And obviously, this is a situation where hopefully we can improve that with some simple machines. So, the request for proposal to the Gates Foundation had some criteria. For example, increasing the number of pits per day that can be extracted. Obviously, having a more hygienic solution. Again, this question of transport in narrow lanes. If we can have a simple machine that can access some of these areas that are inaccessible to vacuum trucks, that will be really good. A two-person operation. You don't want a big, heavy machine that has to be operated by many people. And then also this concept of heavy sludge and debris at the bottom of these tanks, especially if it's been sitting there for a long time. Hopefully it will be affordable, it will be robust, it will be made of locally available components. So if it does break down, then there's an easy way of fixing it, and there's an easy way of getting access to parts. And obviously low emptying costs per routine. So about a year and a half ago, Tate was an undergraduate student at NC State University, and part of our curriculum is a senior design project. And Bob Gordon, who was teaching that class that semester, said, okay, what about if we use the minds of our young engineers or graduate students? Now, what about if we give them the Gates Foundation proposals and see if they can come up with some ideas? And so this is actually part of Tate's undergraduate senior design class. Now, Tate looks nice in front here with a tie, and he looks nice cleaned up. But he's actually a farm boy and grew up in the farm and has dug a lot of posts on their family farm. And they usually use a power-curved auger. And so he came up with this idea, and this is the original diagram of the idea, was to basically enclose that screw auger in a tube, and then fit a internal combustion engine. In this case, it's a gasoline engine on top, and then use that to basically extract the contents of the pit. And that was the original design. And Bob and Tate and I wrote that up, and fortunately got some funding to try to start looking at this idea. So here's a little bit more of a blown up picture of the extraction auger. You have again the diesel engine or gasoline engine on top. In the field it will be a diesel engine. And then you have an attachment that basically fixes the power head to the tube, and so it holds the tube steady. And then you have inside your screw, your auger. So you can look up screw conveyor theory. You can come up with equations that people have looked at to develop, for example, equations for discharge. And it's a function, obviously, of a bunch of things, including the screw diameter, the shaft diameter, the screw pitch, which is the distance between the screw, from crest to crest of the screw, if you will. The choke length, which is the distance between the very tip of the auger and where the tube starts, and so on. And so you can apply these equations and come up with theoretical, okay, what are the best type of parameters that we think will work for this situation. In the lab, these are actually the design variables that they tested. First of all, instead of using diesel engine, in the lab we use an electric motor so that we can have control of the rotational speed, because we wanted to see what the effect was of RPM. We also tested it in a vertical orientation, and later on found out that actually if you incline it, it's actually even more efficient at discharging. And so the vertical orientation with the screw auger, standing up, is actually the best or the most conservative situation. There are other variables, for example, submergence, the choke length, the rotational speed, and the length of the auger. And during this lab test, there were several data points that were collected. And this is a picture of the screw auger. We're basically just recirculating in a drum just to demonstrate, how it works. And for our testing, we really didn't have access to pick the machines where we were. So we tested a variety of different concentrations of simulated sludge, basically mixing different concentrations of clay, bentonite, and making thicker and thicker solutions of that bentonite solution. So here's the rate versus viscosity diagram, basically showing the thixotropic properties of human stools as well as our simulated waste. The purple line at the top is actually data from the lab here in KwaZulu-Natal with Chris Buckley's group, and that's what we were trying to approximate. If you keep adding, increasing the level of bentonite from 5%, 3% to 5%, 7% to 8% bentonite, you can see that it's going up in terms of the viscosity versus shear rate curve, but it doesn't quite approximate the actual human stool. Unfortunately, as you keep adding more bentonite, the incremental change becomes smaller and smaller. And so we were at that point where we keep adding more and there was not a lot of change. And so in subsequent tests, for example, in the field, what we did was we just added other kinds of things, 7% bentonite, for example, horse manure or straw, to simulate the waste. So as you increase the rotational speed on the x-axis here, and again this is with the motor, so that's the RPM, has even better performance than the 6% and the 5%. So this gives us hope that actually the thicker the waste is, obviously to a certain maximum. But if we had a thicker slurry, we can actually get better performance in terms of the flow curve. Now, Tate also measured the head. He also had a setup where you can measure the pressure along the different points of the auger. And what this is showing is, again, the thicker mixture, 7% bentonite, you actually produce a higher head. But if you notice on the y-axis there, that's in centimeters, so it's really not much head. Basically, you're pumping to the length of the screw auger. You're not producing any pressure to pump it out uphill, for example. So it was just another experiment to show we can lift it up, but we can't really pump it beyond where we actually physically have the screw auger. Now we can also use those equations that I showed earlier and calculate an efficiency, and we call this the vortex efficiency. It's basically based on using the equations to define the ideal flow rate or the perfect flow rate for the conditions we have, and then compare that with the actual flow that we were getting. So again, efficiency increased as we increased the thickness and viscosity of our simulated sludge. And we were getting somewhere like 20% in terms of the efficiency. But again, this is comparing it to a perfect or ideal extraction auger. And at the bottom, what you can see is that as again you increase the RPM, you increase the flow rate, and if you pick any point there, for example 300 RPM, which is what you would typically get from a diesel engine, the rotational speed of a diesel engine, you'll see you get something like close to 50 liters per minute. So in the lab, what we showed was the flow rate and the outlet pressure increased with viscosity and rotational speed. And this flow rate of 50 liters per minute or 13 gallons per minute at 300 RPM, which would be typical for a diesel engine, can empty a 1 cubic meter pit in 30 minutes. So we thought, okay, that actually looked really promising. We also found out that submergence has a small effect on the flow rate, and that the pressure produced at the outlet is not enough to pump the waste uphill. And there's a picture of sort of like the slurry. I guess you can imagine that. And I do have a video, which I hope will work. It was working earlier in the lab, a couple of doors down. Well, if we were seeing the video, and actually we can see if we can show the video later. If you're interested, we'll find another way to show it. It's a short video, but it's starring tape, and they're out in the field, and they have the actual prototype where you have the diesel engine, and it's a two-person operation, and they had this bentonite mixture, the thickest we can make it, and then they were adding horse manure and some straw, and it was actually pumping quite well. It was doing great under those conditions. So, if you're interested, we can show that video later. So here's a scenario, and that's a picture from the video on the right, and that's Tate and Brandon doing this in the horse farm, and that's a scenario that you can think about in terms of how you would use the extraction auger. So it's a two-person operation. And here's another scenario. I don't really want to call it a business model, but perhaps if you have a franchisor or a collection agent, and they can put it together and put it on an auto rig, something like this. And if the final treatment or final disposal place is close enough, then they can get there using this auto rickshaw. Maybe it's 15, 20 kilometers. And if it's longer, you can have a transfer station or another truck that will take it longer distances. And several people have talked about business models already. So here's in our mind how we can try to incorporate this technology in that kind of scenario. Now, about a month ago, after the Delegates Seattle Fair, we actually got in touch with PID, Dave Steele, and Chris Buckley, and they sent us some material. And again, we didn't know that this existed, that they were doing all this work. And they actually had tested a pit screw auger technology, which if you were here this morning, you heard Dave Steele talk about this. And listed a lot of positives, including relative high flow rates, lifts more solid waste, simple to use, simple to understand. But there were also some negatives. For example, the fixed length, they found out that their prototype was heavy, so they needed a tripod mechanism to do this, and it was difficult to clean. And so we wanted to address some of those and came up with some ideas. And some of these ideas were also ideas that they had expressed. So, for example, if this negative of fixed length, if you have a deeper pit, you can actually envision that you can couple several sessions of this together, and you can do this on site. So you can get into the site, and then you can do it. And the way we have it right now is in 4-foot lengths or 1.2 meters, and the idea is you can make it 4 or 8 feet. One of the main issues that they had with their prototype was that they found it was heavy. Well, our extraction auger is actually made of plastic. It's a commercially bought HDPE screw. It's a little bit lighter, so about 25 to 40 kilograms. And the other thing is that it's freestanding once in the pit. And if you have seen the video, you would have seen that it was basically just sitting there. You don't need a tripod. You can put a metal support piece, a rounded piece at the bottom. It can sit basically at the bottom of the pit, and it's just basically, you don't really need to carry the weight of the auger, and it's probably half the weight of the metal screw that they have. So other improvements, it may be a little bit easier to clean because it's made of plastic. It's HDPE. And the other option also is, and this is something that we're working on at the moment, is including a reversible drive on the diesel engine. So what that means is that when you're done, there's still basically the sludge inside your screw auger. You reverse the drive and you push back that remaining volume back into the pit. And that makes it easier for you to lift up the entire auger. This question of compaction near the top can be addressed by, for example, making a Y fitting, which I think the prototype from BID already had, and also incorporating reverse sliding. So near the top, right here, you reverse the orientation of the screw, the direction of the screw. And so you're actually pushing it out on that Y fitting instead of compacting it in the top. So what's the status of the current prototype? We believe we're ready for what we would call wet latrines. And so more of the wet sludge, maybe from core flush toilets, maybe from pit toilets, maybe some of the toilets that are common more in South Asia and Southeast Asia. There are issues with dry pits. Again, if you have pits with high trash content, lots of stuff in there, it seems that there's still going to be a lot of manual excavation that has to happen before you can use any technology there. We're thinking of other designs to address those, but we think that the prototype we have is ready to go to the field for what we would call the wet latrines. Maybe even slightly drier. So currently we are modifying, making designs, alterations to the design, and constructing these in the lab. And we are actively looking for partnerships. We started conversations with a few people, but if you would like for us, for tape, to actually go to your place and try this out, we can arrange that. We'd really like to make sure that this works in the field and try it for both all kinds of pits. We believe that we'll have more success maybe with the wet pits, but we want to try it on the dry pits too and see if it does work or not work, and what can we do to address those. So, future scenarios would be looking at how you would set this up as local businesses. And again, a lot of you would have experience with that and would like to partner with you. So finally, we actually have a survey that we would like to get as many people to take. And there are 3 ways to take this survey. You can go to this website. It's surveymonkey.com/s/extraction auger. It's an online survey. I would like to get some more background information, more data from actual few people who've done this work. If you have a slow connection, you can send email to Bob Borden, that's his email address, rcborden@ncsu.edu, and he can email you a copy of the survey, and you can email that back. And also we brought some paper copies with us, so if you would like to fill that out now, it takes about 20-25 minutes, maybe even faster, to complete the survey. We'd like to get some data because again, we know it works in our setup, but the real test is the real field. So, thank you.